Yes. Dear colleagues, I'm happy to start out today's talk. Our speaker, Theodore Popelensky, will tell us about relations in the cohomology of Hopf algebras. Let's welcome.
Thank you very much for the invitation. I will speak about relation in the cohomology of Hopf algebras. And this approach was based on a spectral sequence which was introduced by Viktor Matveyevich Buchstaber many years ago, and in our recent work we found some applications, new applications. So let me start from short reminder of why we have two titles, I don't know. So what is a Hopf algebra? It's very rich structure which consists of associative algebra, so it has multiplication and unit, and it's also at the same moment as coalgebra, co-associative coalgebra. It has coproduct and co-unit. In modern language, it also has anti-homomorphism psi, and everything which is written here is compatible in a certain way. And one of the most important formulas is that multiplication is a coalgebra homomorphism, or equivalently, co-multiplication is an algebra homomorphism, and both statements can be represented by a single formula that coproduct applied to product of two elements x and y is a product of two elements. One of them is delta of x and another one is delta of y. In topology, A is usually graded, and algebra, in pure algebra, it may be not graded. That's why for a long time people did not recognize that anti-homomorphism should be part of structure, because in topology, Hopf algebras which appeared in topology were either commutative or co-commutative, and if the algebra is graded and connective, then anti-homomorphism psi can be defined inductively by grading, and it's not necessary to introduce it into the definition. But nevertheless, what we see here is more or less modern point of view on the Hopf algebra. Let me tell you a few words about history, because it's quite funny to learn what happened there. The theory of Hopf algebra goes back to the work of Heinz Hopf über die Topologie de Gruppenmannigfaltigkeiten and blah blah blah. So it is a very interesting story about this paper, because it was written something in 1939 and was submitted to Compositio Mathematica, but the journal was closed, and the paper was forwarded to Annals of Mathematics and was published in 1941. The problem which was discussed by Heinz Hopf was about cohomology rings of manifolds. It's quite interesting that he was interested in cohomology of smooth manifolds, such that it has non-trivial multiplication, which is not an algebra multiplication. It's just a map from m times m to m, but it should be non-trivial in the following way. So if you fix first argument, then you obtain map from m to m, and if you fix second argument, you again obtain map from m to m. And requirement was that both maps should have non-zero degrees, not necessarily coinciding, but non-zero. It was the first work where co-multiplication diagonal in cohomology of topological space appeared. Actual development of Hopf algebras as an algebraic structure begins more than 10 years later. There are two different two different directions. One of them was in topology, another one was in pure algebra, and first topological work on Hopf algebra was work by Armand Barrel. Later it was made by Milner, by some other people, and in pure algebra it was work by Dieudonné, Pierre Cartier, by Hochschild, Gabriel Katz, and some other people which was not mentioned on this slide, but there are plenty of people who worked in both directions. This first period of working on this theory was culminated in two big texts. First text was text in topology, which was written by Milner and Moore. It was published as a paper in 1965, but actually it was available much earlier. And another it was about graded Hopf algebras. Yes, on theory of graded Hopf algebras. Algebraic context was by Swidler. It's a very famous book. I guess it was the first book on Hopf algebras. And at this moment, then these texts were written, people has the following examples. Cohomology of spaces with multiplication. It was so-called H spaces. Another one was rings of function on algebraic groups, rings of regular function on algebraic groups. Another one was group algebras of discrete groups and universal enveloping algebras of Lie algebras. These were first examples. In 1958, Milner found that the algebra of stable cohomology operations in ordinary cohomology is a Hopf algebra. So he found that there is a well-defined coproduct there, and also there is an antipode, and actually the paper which was called as the Steenrod algebra and its dual, on the first paper of this on the first page of this paper, it was mentioned that the most important result of this paper is the proof that algebra of stable cohomology operations is a Hopf algebra. Actually, we know that there is not a single algebra, but there are a bunch of Steenrod algebras. For each prime p, we have one algebra of stable cohomology operations. Time went on, and people found much more another example. So there are a huge collection of examples of Hopf algebras which came from combinatorics, Giancarlo Rota, and so on. The most striking, well, what is important to say that the examples which were mentioned here are either commutative or co-commutative, and then all examples of Hopf algebras which are not commutative and not co-commutative were absolutely artificial, not natural. And the first natural examples of such objects were appeared after works of Drinfeld and Jimbo on quantum groups. But the example of non-commutative and non-co-commutative algebra was known. You can found it in a book of Swidler. It is not mentioned that the structure is not commutative, not co-commutative, but the example is there. Okay. So let me say a few words. So most important example today will be Hopf algebra of Steenrod algebra A2 and its dual Hopf algebra A2 star. Let me remind you a few results about that. So A2 is generated by so-called Steenrod squares SQI for each I greater or equal to 1, and SQ0 is also considered, but it is an identity. There is a complicated Adem relations. So in the second line you can see this formula. We don't need it, but we should have a look at this formula. And the action of stable cohomology operations and Z2 cohomology of topological space is described by several properties. They are not mentioned here, but there is a Cartan formula which is a source of co-multiplication and in standard algebra, which you can see here. And important result in the paper by Milner, which was mentioned earlier, that dual Hopf algebra A2 has much more simpler structure than original standard algebra. Namely, dual Hopf algebra is a algebra of polynomials on on symbols xi, where the degree of element xi n is equal to 2 to the power of n minus 1, and the co-multiplication coproduct is given by the formula which you can see below. The same description is available and was obtained by Milner for primes which are greater than 2, but we don't need it, so I omit the formulas, but the description is more or less similar. The dual algebra to AP is a polynomial algebra on certain generators and tensored with some exterior algebra on some other generators. So that as an algebra, dual algebra is very, very simple thing, but coalgebra structure is more or less complicated. Well, what do we want to speak about? We want to speak about cohomology of Hopf algebras and relations inside that, and the example which I want to present here is a cohomology of the standard algebra A2, and let me remind you some basic results about results were not kind of toy maybe. It were intended to solve very complicated problem, the problem of Hopf invariant. We know that there are many equivalent formulations of the Hopf invariant problem, Hopf invariant 1 problem, because the question was for which cases Hopf invariant can be equal to 1. So I don't want to give a definition of Hopf invariant, but I want to say that the question in which cases, for which dimensions Hopf invariant can be equal to 1 is equivalent to some purely geometrical questions. For example, for which n the sphere S1 is an H space, in which case homotopy multiplication. Another reformulation, for which n the sphere Sn minus 1 is parallelizable. We know examples. S1, S3, and S7, they are all parallelizable because these are the spaces of Lie groups. That's why they are parallelizable, but there are no other cases. Another interesting statement is for which n the space Rn is a division algebra. It means that you can define a linear product. You don't require any properties like commutativity, associativity, existence of unit. You don't need anything except only one property, which I will write now. That division algebra means that if you multiply A by X and you write, this is an equation, the product of A and X is equal to B. Product of X and A is equal. They could be different. For first equation, for second equation, resulting x's can be different, but they should exist provided A is not 0. Because obviously you cannot divide by 0. So And another formulation in terms of Adam's spectral sequence is which elements Hi survive to E infinity, a limiting term of the spectral sequence. I will define elements Hi a little bit later, and the answer was obtained by Adams, and the answer is that n is equal to 1, 2, 4, and 8, which corresponds to real numbers, complex numbers, quaternions, and octonions, and the corresponding I is 0, 1, 2, and 3, which are logarithms of n on the base 2. Well, from relatively elementary considerations, it follows that if Hopf invariant 1, that if the dimension n, there is a map with Hopf invariant equal to 1, that n should be equal to power of 2. There are many proofs, more or less elementary. One of them is discussion of indecomposable elements of the standard algebra A2. Maybe you can calculate Stiefel-Whitney classes of projective spaces and blah blah blah. There are some other proofs, but these two proofs I like most of others. But before final solution of this question, Adams and his work on the structure and applications of the standard algebra, it was published in 1998 in Communications of Mathematica Helvetica, he introduced a new spectral sequence for computing the stable homotopy groups of a space X. This is famous standard algebra, and the second page of this spectral sequence is a X groups calculated for standard algebra AP for two modules, cohomology of the space X with coefficients n ZP and ZP module. It's a very purely algebraic thing. So differentials in this spectral sequence is very complicated, very difficult. In some cases they can be found. I will tell you a few words about that a little bit later. And this spectral sequence is sufficiently complicated because it converges not to the stable groups of the space X, but to P completion of this group. It means that in this group there is a filtration such that successive filtration quotients are the limiting groups A infinity. When you need to use the relation that T minus S is equal to N. So if you're interested in homotopy group, stable homotopy group with number N, so then you should follow the limiting groups A infinity with grading T and S such that T minus S is equal to N, but the intersection of these filtration terms is not zero. It consists exactly of elements of finite order, which is coprime to prime number P. So roughly speaking, the Adams spectral sequence for prime P founds torsion-free part of the stable homotopy group and also P prime component of the stable homotopy groups. After establishing the spectral sequence, he found that if two spheres of successive dimension after taking power, so S2 to the power of n minus 1 and S to the power S in dimension 2 to the power n minus 1 plus 1 minus 1, if both of them are H spaces, then n should be not greater than 4. For this purpose, he needed to calculate cohomology of the standard algebra. So if we speak about Hopf invariant problem or stable homotopy groups of sphere, you don't need to calculate this group for space X, but you need to calculate it for very specific space, for a sphere. And before we proceed, let me tell you some words, because it's good to know that the final solution of Hopf invariant problem was obtained 1 year later in the paper on Hopf invariant 1 by John Frank Adams, and he proved it. It's a very long paper, I think 80 pages long, and I'm not sure that many people on the earth can know the details of this paper. It's a very long paper. The problem was solved, but what is interesting, maybe in a year or two, they found very simple proof by methods of topological K-theory, and the standard proof now is to use, so maybe in any textbook on vector bundles, topological K-theory and Adams operations, there is a simple proof. It is half page long. It's very elegant, and it was not obtained by methods using Adams spectral sequence, but nevertheless, before that proof using topological methods, there was a proof obtained by Adams, and very long.
I think the simplest
Let me
proof
tell you.
is, excuse me, I think the simplest proof is that we have powers of 3 and powers of 2, something like that. So we have some formulas for Steenrod operations and nothing more. And so that some powers of 2 are 3 minus 1 are divisible by powers of 2, no? As far as I remember, there was a book by K-theory.
No. He used Adams operations like this, and they should commute, and they were calculated on a very specific element, and they after that you obtain contradiction, and from
Yes. But this is the matter of
but
how a power of 2 minus 1 is divisible by a power of 3.
yes,
Say 81 minus 1 is divisible by 16,
you
something like that. But further, but it is later, it is not so.
this has nothing to do with standard algebra. It's so-called Adams.
Yes. This is uh, uh, mm,
These are Adams operations, nothing to do with standard algebra.
okay.
But I will tell you some interesting thing a little bit later. So what Adams did, so he performed first calculations of generators in cohomology and relations in cohomology, and this is thing which I want to discuss right now. So first of all, we calculate the first cohomology group, which is X1. What is important that this group has additional X has two gradings, S and T. So we discussed the case and S is equal to 1, the first line of the spectral sequence. These groups are 0 except the case and T is power of 2. For T, which is a power of 2, these groups are cyclic group of order 2, and the generator is HK, represented in the Kobark complex by very specific element which is written here, and this is it is related to the very simple statement that Hopf invariant 1 can be only in this dimension. So we have in second page of the Adams spectral sequence, we have generators HK, which is in the first line. I will show you a picture a little bit later. And the question is, which of them survive until infinity? Which are cycles of all differentials? And from the result of Adams, so maybe Adams and Atiyah and some other maybe topological K-theory proof. So we know that HK for K greater or equal than 4, all of them do not survive until infinity. So only 4 H's survive, and these are H0, H1, H2, and H3. Only them survive until E infinity. All other generators in the first line disappear. Well, okay, so the question is, what can be said about it? It is a very basic thing. So the people asked what happens in the second line, in the second cohomology group of the of the standard algebra, and it appears that this second line of the spectral sequence is generated by products of elements HK, but there are relations. There are relations. One of them is that this cohomology algebra is commutative. This is over Z2, so you don't worry about sign. So HI times HJ is equal to HJ HI. It's not a surprise. We need to have such a formula. But the relation which we want to see is that if you multiply two h's with successive numbers, the product is 0. And Adams proved that if you want to consider an additive basis and second cohomology of the standard algebra, you can write the elements hi squared and hjhi with numbers which are different at least by 2. Indices which are different at least by 2. So we can have a look at the second page. This one is x st of a2 z2 z2. Have a look on the gradings which are represented in this picture. So we have s here, and here people usually write t minus s, because otherwise this picture will be distorted and will occupy too much place on the screen. So let me repeat that. In the first line you have h's. On the second line you have some other elements which are products of h's, and you have no elements of the form h1 h0 h2 h1 h3 h2, because all of them by Adams' theorem are zeros, so there are no such elements here. With elements hi squared, there is a very famous result. There's the theorem about Kerver invariant. So the question was, which h squares survive until infinity? And there are some geometrical construction of framed manifolds with Kerver invariant equal to 1, and result by Hill, Hopkins, and Ravenel that for I greater or equal than I believe 7, these elements do not survive at infinity, and for I less or equal to 5, people know that they survive until infinity. So there are examples and of framed manifolds, and the question, it was solved recently. Well, is it 6 or 6? Yes, in dimension 126. This element sits in x to 126, and the question was, it was obtained maybe at most 2 years ago. 3 Chinese mathematicians have proof that this element survived until infinity, and the proofs, as it was announced, the proof uses all the powerful tools from recent developments in stable homotopy theory, such as motivic homotopy theory, so motivic Adams spectral sequence, some results from synthetic spectra theory, and so on, so on. So it uses everything that people have now in stable homotopy theory. Very interesting result, but maybe it should be checked. I'm not sure if it's already published, but a few months ago there was an activity that the authors of the result explained their proof in details, and it was there was a bunch of attention to these results. Very interesting thing. So, but we proceed further. Adams also represented he needed some calculations for third cohomology group, for X3, so for the third line in his spectral sequence, and among elements which are in that line, he found some new relations. But what is interesting, why we discuss this thing, that the cohomology of the String-Root algebra is not generated by elements HI. There are some other elements there. And first of them, as I guess, I made some research in literature, as I guess, the first time these elements appeared in literature was paper by Novikov. I guess it was his first paper published in '59. He found that there are some non-zero elements which I denote by Ci. They are not described by Adams' theorems. They are not product of Hi, Hj. So they are not. This element is not product of elements H from the first line of the Adams spectral sequence. Only 8 years later, I guess that Wank didn't know about Novikov result because he gave no reference. He proved that these elements Ci are represented by non-trivial Massey triple product, which is written here. And another result was that if you use elements Hi, Hj, and Hk described in Adams' spectral sequence, form products as it was written in Adams' paper, and add elements Ci there, you will obtain an additive basis and third cohomology group. Actually, Wank found proof of Adams' theorem about Hopf invariant 1 using by calculations of fourth homology group. So having calculated some elements in this group, Wank was able to prove it is also very short proof, maybe 5 lines. He proved that second differential of Hk is 0 for k greater or equal than 4. So if Adams had sufficiently developed homological algebra, and provided he was able to calculate X4, then he will obtain very simple proof of his Hopf invariant 1 problem. The proof of Wank is very straightforward, so you don't need to. So actually, if you want to know some information about higher differentials in Adams' spectral sequence, you need to apply some topology. The topology is used there, but in very, very simple and very elegant way. But after that, you need to prove that differential is 0. It is very, very elegant and simple proof. So, but I guess that this proof is far less known than the proof by methods of topological K-theory. Okay, let's go further. So looking at the relations Hi, Hi1, so there is a product Hi plus 1 times the Hi is 0. So there are 4 Massey products which can be defined. This one, this one, this one, and this one. I will speak about Massey products and their definition a little bit later. Just now you can trust me that there is a specific operation of such type. It could produce some new elements, but there are very simple relations there. And this is a topic of my talk, because there is some regular procedure to find at least some of relations between Massey products and usual products and so on. Some of them obviously are encoded in so-called A infinity structure, but now I want to speak about Buchstaber spectral sequence. It will appear a little bit later. So we have 4 Massey products, but these Massey products do not produce new elements because 2 of them give you already known elements and 2 other Massey products give you zeros. So nothing new. Okay, let's go further. So I like this example. So Adam's spectral sequence appeared to be a very useful tool in algebraic topology for computing stable homotopy groups. And it is quite surprising that then student is learning topology. The people tell to the student that, okay, we have Adam's spectral sequence to compute stable homotopy groups of spheres. The problem which is not solved at all. So we have some calculations, huge calculations. The amount of results cannot be described in a few words. So there are huge tables, blah blah blah. But nevertheless, the first result, which appears to be very important, was calculation of unitary cobordism rings. But at the moment that Novikov and Milner proved the theorem about structure of complex cobordism ring, there were some other rings which were more or less calculated. Unoriented cobordism ring, which was calculated by Tom. Special orthogonal cobordism, or cobordisms of oriented manifolds, which were more or less calculated by Averbuch and Wall. And some other theories, but it appears that unitary complex cobordism ring is a new thing, which was not, the theorem which is written here, which is presented here, was proved exactly by using such a powerful tool as Adam's spectral sequence. So both of them, Milner and Novikov, used Adam's spectral sequence, Hopf algebra structure of standard algebra. So also they both reproved, they found new proofs for already known results. So they proved that unitary cobordism ring is a polynomial ring on generators Y with number k, such that degree of this element is 2k. Also, they found manifolds which represent the generators, and so on, so on. Surprisingly, the generators are not complex projective spaces, but nevertheless. So, what happened in a few years? In a few years, oh well, we can skip it. It's not necessary. So, in a few years, maybe it's written in Russian. So it is a report about International Congress of Mathematicians, which was held in Moscow in 66. There was an interesting story that Novikov went to the room and told that he didn't want to speak about. He didn't want to give a talk which was announced on characteristic Pontryagin classes, and he gave printed copy of this talk and told that he wants to speak about completely new thing, which was published a little bit later as a huge, big paper, which is called Methods of Algebraic Topology from Viewpoint of Cobordism Theory. So actually, what he did, he found that a unitary cobordism ring produces complex cobordism theory, which is much more useful, much richer than the ordinary homology. He found the structure of algebra of cohomology operations. He found many interesting things. So here you can see some citations from the paper. What he wrote. He wrote that during development of his theory, he found that there are some new effects and new promising perspective which were not visible in ordinary cohomology theory. And history of development of algebraic topology proved that he was absolutely right. So the short list of his achievements in this paper, the list of achievements is not complete. It's much longer. I would say that these are only 5 points, 5 items which I mentioned here, but maybe it's 50 items. Very much more information in that paper. So he introduced the algebra of stable cohomology operations and calculated it. Inside this algebra of stable cohomology operations, he found very important, much more smaller algebra, which is called Landweber-Novikov algebra. The name of Peter Landweber appeared here because Landweber at the same moment developed the same algebra using more or less close ideas. Novikov found the rule. So what we see, that elements of from the complex cobordism of some topological space can be multiplied by elements of the scalar ring, cohomology ring, omega u. So you can apply to elements in u of x. We have two things which act here. So a ring of scalars, and on the same, also on the left, there is an action of Landweber-Novikov algebra, and these two actions do not commute, and Novikov found the rule for commutation. And also he constructed so-called, now it is called Adams-Novikov spectral sequence. The idea was, roughly speaking, it is based on the idea of Adams, but you need to develop a huge portion of homological algebra. You need to develop theory of convergence. You need to know what is the space to which the spectral sequence converges. So there are a bunch of questions which should be solved before one can use Adams-Novikov spectral sequence. And also his result was about computation of the first line of his spectral sequence converging to the stable homotopy groups of spheres. What is important, the spectral sequence based on complex cobordism theory converges to the stable homotopy groups without any localization. So it converges to integrally over integers. So the thing which is written here, x to 1 over Landweber-Novikov algebra, it should contain all the information about torsion in stable homotopy groups. And it's not surprising.
Excuse me, and does it distinguish between, for example, Z2 cubed and Z8?
I will tell you a little.
Okay.
Okay. So this thing, it's also converges to the quotient by corresponding filtration. Yes. So it loses some information. So it does not. It converges to some graded object which is related to some filtration in stable homotopy groups, but nevertheless it can see some element of prime order, but so 2 to the power of something. Okay, so in some cases he distinguishes order 2 to the power of something with 2, 2, and 2. Okay. So to see that this thing is difficult, I can tell you that Ext1 contains the image of, so it's technical, so we can skip it. Okay, let me show you one. Yes, so as you can see, Bernoulli numbers appears during calculation of this first line of Adams-Novikov spectral sequence. It means that the calculation was difficult. Every time in topology we see Bernoulli numbers, it means we have very difficult theorem. I can tell you that calculation of second line was performed, I think, 10 years later by Miller, Wilson, and Ravenel, and only after localizing by prime number greater than 2. So they introduced so-called chromatic filtration and so some periodicity things, but the calculation of second line of the Adams-Novikov spectral sequence for spheres based on complex cobordism theory takes 10 years. So let me tell you a few words about Landweber-Novikov.
The second line, you mean second page?
It's quite fun. Yeah?
The second line, you mean second page?
Oh no, second line. So the thing
Okay.
which is written here, it is second page, but second page is a huge object, and Novikov calculated this one, and people needed 10 years to calculate this one. This is a first line, 1 start 2, yes, and this one is a second line. Nobody knows what is the second page of both spectral sequence. Nobody calculated cohomology of Steenrod algebra, and nobody calculated cohomology of Landweber-Novikov algebra as a whole object, only up to certain gradings. Well, so let me tell you a few words about Landweber-Novikov operations, because it's very elegant construction. So what is funny, we have characteristic classes in complex cobordism theory. It's normal we have characteristic classes because there is an orientation of complex line bundle in this theory. That's why we have first Chern class of tautological line bundle over CP1. Then we can proceed by standard procedure. So we have first Chern class of a line bundle over CP infinity. Then we can produce Chern classes over classifying space of a unitary group. And then passing to symmetrization, we obtain the class which is in complex cobordism of classifying space. And then it's a miracle, we have Thom isomorphism. So by Thom isomorphism, this element can be moved to this algebra, complex cobordism of the Thom spectrum MU. And then we obtain a cohomology operation. If you have an element in complex cobordism of Thom spectrum MU, then you have a cohomology operation. What is a miracle? Miracle is that if you take S omega 1 and take a composition with S omega 2, one could think that it should be something complicated. But it appears that this is a linear combination of S omegas where these things are integer numbers. It's a miracle. It's not so. Lambdas are not elements from the scalars. They are not elements of ring of coefficients of complex cobordism theory. It's just integer numbers. There is an inductive procedure to found them, so it's not a very difficult problem. It's a problem of pure algebra, but it means that S omegas generate an algebra over integer numbers. These not appear to some other cobordism theories. So if you localize complex cobordism theory at prime P, you will obtain so-called Brown-Peterson cohomology, very important tool in modern stable homotopy theory. But the operations in this Brown-Peterson cohomology does not allow you to found an analog of Landweber-Novikov algebra. That's why, from one point of view, local calculation became a little bit simpler, but since there are no Landweber-Novikov algebra, the calculations are not straightforward. Okay, nevertheless, so let's go on. This is a picture. That's why people like Adams-Novikov spectral sequence for prime greater than 2. So as you can see, the second page of the Adams-Novikov spectral sequence are much more sparse than Adams spectral sequence. The elements which disappear during calculation of the second page, so it means that everything here should disappear during calculations of differentials in Adams spectral sequence. So it means that it requires some additional algebraic work, but Adams-Novikov spectral sequence gives you a way to not to think about those elements. There are no elements of such type in the second page. That's why people like Adams-Novikov spectral sequence, at least for primes greater than 2. But it's quite funny to know that for p equal to 2, these two spectral sequences both of them still used in modern computations. Both of them are not so sparse, and they provide some important information. So people still calculate Adams spectral sequence for p equal to 2. Okay, so second part is about Buchstaber spectral sequence. What approximately...
Это не телефон.
Sorry?
No.
No, okay. So approximately at that time, then it was in 70. Buchstaber was trying to find a way to describe the second page of the Adams-Novikov spectral sequence, and he found very interesting thing. He found the following, that if you look at the ring of coefficients of complex cobordism theory, it is a free object. So if you take a tensor product with rationals, there is an embedding of rings. So ring of the complex cobordism ring is embedded into the complex cobordism ring tensored with rationals, and this embedding is compatible with the action of Landweber-Novikov algebra. Buchstaber found an intermediate ring, which he denotes by omega u of z. He described it in terms of manifolds with specific properties of characteristic numbers. We don't need it because this is not necessary details, but what is important that you have ring, which is a coefficient ring of complex cobordism theory. You have a rational version of it. So let me remind that this is an integer of classes of such type. Here you have rational coefficient. But actually, there is a very important intermediate ring, which is also a module over Landweber-Novikov algebra, and a kind of miracle appears that this intermediate ring is isomorphic to the dual Hopf algebra to the Landweber-Novikov algebra. So obviously, we have dual Hopf algebra. It's nothing difficult. It's more or less obvious, and it sits between these two rings. It's also more or less clear, but he found the description in terms of characteristic numbers, and the description is very, very elegant. Why we are interested in this algebra? Let me explain you. So we want to calculate this object. And if we change the coefficient ring on the second argument by, we can write here, there's one or S dual, then this is zero. This one is trivial, because if you calculate cohomology of the Hopf algebra having on the second argument its dual Hopf algebra, then these X groups became trivial. Except if S is equal to T and equal to 0, it will be, I guess it's X is equal to 0 and two integers. Well, what it gives to us? Victor Matveyevich introduced very specific filtration, which is written here. So the filtration starts with, this is N0, then he embedded into N1, and definition of N1 is as follows. If you apply any operation from Landweber-Novikov algebra from which has degree greater than 0, so we can write it in this way. So you take Landweber-Novikov algebra, right here plus, which it means that it is ideal of augmentation, then you apply it to N1, you obtain subspace N0. So N1 is maximal subspace with such a property. So N2 has a similar property. You take an element such that you apply operations of non-zero degree and obtain element in N1, and so on. So the formal definition is written here, and what is due to the fact that everything is graded. This is a filtration which starts from the coefficients of complex cobordism, and it converges to this algebra, which is omega u of z, just due to the grading. So since everything is graded, this thing converges there. There is an example in Lie algebra theory that if you try to define something like this for universal enveloping algebra, say for SL2, then nothing happens. So the filtration will not converge to the whole object. But here we have this convergence. What is important here? Why we interested in this property? Very simple. If you consider successive filtrations, if you take as NP quotient by NP minus 1 as written here, then the action here is trivial, obviously, because elements of the Landweber-Novikov algebra of positive degree shift elements of NP to the element of NP minus 1, and we take a quotient with NP minus 1. So the module NP quotient by NP minus 1 is trivial as S module. And this provides us with the following very simple spectral sequence, very elegant one. So consider standard complex which computes this thing. For example, it can be by resolution. And since this standard Kobar resolution complex computing this, not resolution, sorry, resolution is a cyclic, so we use standard complex computing these groups. So this complex is functorial in the argument n. So if we have a filtration, in complexes. So it starts with this one and finishes with one. This one is a cyclic. As I already told you, if you calculate cohomology of the Hopf algebra with coefficients in its dual, then you obtain 3 zeros, except zero grading. So in this case, we obtain 3-graded spectral sequence with trivial limiting term. such that successive filtration terms are trivial S modules. This is a picture. This is a picture. So let me tell you, the grading is not written here. Okay, the grading is as follows. So we want to go here. So this spectral sequence, it is three graded. So there are two gradings, P and Q, which represent together number S, and the third grading is T. So T is not represented on this picture, it goes in orthogonal direction to the screen, but P and Q plus P are represented here, and the differentials go in this way, as you can in this picture. You see the differentials. What are K? K, P is NP quotient and P minus 1. And what we see here, let me explain you the picture. So the first page of this spectral sequence can be calculated by means of homological algebra, and it consists of X over Landweber-Novikov algebra with integers as the first coefficient. And what is important, on the first column, zero column, you still have coefficients which you needed to which you consider when you calculate Adams-Novikov spectral sequence. So the first column, zero column, is the thing which you are interested in. So this is Adams-Novikov spectral sequence, second page. But what is written further? These are very much more simple groups. This is the successive quotients and cohomology of Landweber-Novikov algebra with coefficients in these quotients. But what is important, S does not act on Kp, because we constructed the filtration in such a way that Landweber-Novikov algebra does not act on the successive quotients. It's very, very important. But what is bad about this thing? The bad thing is about that in complex cobordism theory, it is not, the calculation of these groups Kp is not available until this moment. It's not there are some results. Let me tell you what the results are. So Nikolai Panov calculated the group N1. The result is difficult because the first differential in the Buchstaber spectral sequence gives you an isomorphism between these two objects. So first line of the Adams-Novikov spectral sequence is just quotient N1 by N0, and Panov found some specific description of this group N1 for quotient by N0. So he founds a new calculation of the first line in the Adams-Novikov spectral sequence. It was a very important result. A little bit later, Shakurov found some partial computation of second line. It was more or less at the moment when Miller, Ravenel, and Wilson published their paper on second line of Adams-Novikov spectral sequence localized at prime P. Well, and they found some partial results on computation of second line of Adams-Novikov spectral sequence, and found some new elements which represented as Massey products of elements from first line. So recently, Viktor Matveyevich and me, we have developed general case of such a spectral sequence and found some specific applications, and one of them I want to show you today. The idea is as follows. We consider general graded Lie algebra. We don't care about Landweber-Novikov. We consider general case. So we have a Hopf algebra, which is graded and is connected, and we ask that zero component is equal to R, and we assume that R is a field. Over a field, the calculation became a little bit easier. So now we define filtration. So we start from N0, which is ground field. And then we define successive filtration in such a way that action of the algebra A on the quotient is trivial. For this purpose, we do the following. We take an element X in the dual algebra, consider its comultiplication. It is a sum which consists of two elements which should exist in this formula because there is a co-unit. And also we have elements here. So we request that the first part of this tensor product belongs to the previous filtration. For the case of Landweber-Novikov algebra, this filtration coincides with that one which was considered by Buchstaber in his paper in 1970. This filtration actually is called by filtration of co-powers of co-augmentation ideal, and people uses this filtration. For example, in Milner-Moore paper, this filtration was published, yes, but this was not used in this context. So now we consider spectral sequence associated with this filtration. We obtain three graded spectral sequence, which sits in very interesting place if we consider gradings P and Q, first and second one. The third grading goes in orthogonal direction to the screen. So the spectral sequence sits in the corner, which is shown on this slide. Zero column of this spectral sequence gives you cohomology of the object you want to calculate, or the cohomology of the algebra A itself. Diagonal, so the thing which is written on this diagonal are successive filtrations, so quotients of previous filtration by NP, quotient by NP minus 1, and the thing which are written in other places, so except zero column and except diagonal, can be calculated in a very simple way. These are X with coefficient with this module, which is module with trivial action of A, and that's why it can be written as a tensor product of module Kp and the groups we want to found the cohomology of the algebra A. So let me erase it. So the first page of this spectral sequence is actually tensor product of the groups we are interested in cohomology of the algebra itself, and quotients, successive quotients of filtration. And since the spectral sequence converges to zero, we obtain very complicated recurrence relations between differentials of this spectral sequence and groups in this spectral sequence. Let me show you a picture. So in this case, the case of the Hopf algebra over field, what we see on the line, which is, so I applied a fine transformation to represent this angle as this piece of plane. So that's why we have Q plus P on the top and P on the bottom, because the screen is too small to use original picture of Victor Matveevich. So this is a diagonal. So these one are quotients of. So here we see cohomology. So the thing we are interested in is these. So x of R with coefficients and R in the ground field. And in other cages and other places of the spectral sequence, we see just tensor products of the groups in the zero column and zero arrow, in zero row. Differentials act in the directions which are shown by different arrows. And let me explain you what happens. The group H1, there are no differentials, non-trivial differentials which go outside of H1 because there are no non-zero elements to the left. But the spectral sequence converges to zero. So differentials should kill all the elements in H1. So actually, it's a very simple statement that actually H1 is killed by the first differential. It's just more or less a straightforward calculation. If you look at H1, there is some interesting thing. Because the elements in H1 can be killed from this group, or from this group, and from this group, and from that group, and blah, blah, blah. And it means that group H1 is filtered by images of the differentials. Well, and this provides us with very important statement. So it is written, what I already told you, that we can think that differentials in the Buchstaber spectral sequence give you complex recurrence relations between cohomology of the Hopf algebra, which are x's of such form, and quotients of filtration. So to use the spectral sequence, you need to know either one thing or another one. And actually both problems are usually complicated. So this is a statement about differentials. So let me show you this picture in a more clear way. So let's have a zero column. We have a group here which is represented by green color. All the differentials which go out of this green thing are zeros. So there are only differentials which land in the green box. But the green box should be zero if you pass to infinite term of the spectral sequence. So all the elements in the green box should be killed by differentials. So we have a filtration of this in this green box by lift of images of differentials. This provides us with a theorem. The result is not new, which was, this similar statement was obtained by May and Guggenheim, but we have result that the differentials of the Buchstaber spectral sequence realize some specific Massey products. And the statement is as follows. So if an element X from the group XS belongs to filtration K, it means, but does not belong to filtration K minus 1, it means that X is killed exactly by differential decay. Then this element X is a representative, and the statement non-trivial is extremely important, that X is a representative of non-trivial matrix K plus 1 fold Massey product of the form. Matrix means that elements in this Massey product are matrices, where elements A1 and 2 and AK are elements from X to 1, and the last one, well, actually it's not AK plus 1, it's Y. It's an element from the group X S minus 1. If you consider this statement inductively, you will see that all the cohomology of the Hopf algebra A is generated by iterated non-trivial matrix Massey products. It is Very interesting statement. So if you take elements from the first line of the cohomology of Hopf algebra, then you can apply products, Massey products of this specific form, iterate them, blah blah blah, and finally you will obtain all the algebra, all the elements in the algebra. Okay, so time goes on, so let me skip the reminder of what is Massey product. If you are interested in details, there are several classic papers about that. So, for example, original paper by John Peter May about matrix Massey products, maybe some other papers in approximately the same time, but also there is a very interesting and accurate and absolutely understandable exposition by Babenko and Taimanov, matrix Massey products in symplectic manifolds, published in the Sbornik of Mathematics in this year. Very, very nice paper, very well written. So what I want to tell you now, I will explain you how differentials see the relations. Let's have a look at an element which sits somewhere in the middle of the spectral sequence, such that all the differentials on these elements are zero except the last one, which is shown by D2. So this X sits in the column number 2, so that's why I wrote D2. Okay, D2. We have two possibilities. Either this X does not belong to image of any differential. So X does not belong to image of any differential dk. But the element X should disappear. So the only possibility for this element is to cover some element in this box. So if X is not in the image of any differential, so the last possibility for this element is to be killed by differential D2. In this case, the element which sits here should be a triple Massey product. Differential D2 represents triple Massey product. And all the triple Massey product of the form which you saw on the previous slide are exactly in the image of differential D2. So now, let me show you one interesting picture. For example, so this time goes on, so let me pass to the very specific application of this theory. So we started discussing this Massey product in the cohomology of Stringent algebra. This element is of specific form, which is covered by our theorem. It sits in the zero column, and it's not very difficult to show that this element can be represented as a second differential of element of this form. But maybe if this happens, it means that this element with triple Massey product is non-zero, because our theorem says that if element is killed by differential D2, then it is represented by non-trivial triple Massey product. But what happens? The element which is here is killed by the differential number 1, by this element. I know some calculations, but I performed some calculations, so I know so what does it mean for us? It means that the element which I show you on the left, psi 2 to the power 2 to the power of 1, tensor product with hi plus 1, cannot survive until second page. So it was killed in the first page, and in the second page there are no such elements. So there are no differential D2, and it means that this triple Massey product is not killed by the differential d2 because you have no element to which you can apply differential d2. That means that you have no triple product of such type. This triple Massey product should be 0. So this is a way how this differential work with relations in cohomology of standard algebra. Well, also there is a way to represent Novikov elements as elements in the Buchstaber spectral sequence. It just what you do. You consider this specific element, and you know that differential d1 of this element is 0, and also you need to prove that this element is not in the image of any previous differential. So if you look at the picture, it looks as follows. So 0, 1, 2, 3. So the element which is this one sits in this place, and differentials which land in this grading come from this place, from this place, from this place, etc. And it's not difficult to show that there are no such elements which can kill this specific element. Well, so the only way for this element to disappear until E infinity is two possibilities. That first differential of this element is non-zero, or second differential of this element is non-zero. But differential d1 on this element is 0. It's just very simple relation in cohomology of standard algebra. It means that there should be an element here which is there exists C such that d2 of psi2 to the power 1 tensor with h is equal to C, and it is not 0. Otherwise, we obtain a contradiction. So Novikov's elements can be represented in a very simple way in the Buchstaber spectral sequence. So let me finish with very important statement. If you want to use this technique to describe relations in cohomology of some Hopf algebra, you need to know something. Or you need to know cohomology, or you need to know the filtration. Luckily, we have the following description of filtration in the cohomology of the standard algebra. It's very, very elegant. Let me explain you this. So let me repeat that we want to consider to find filtration in the algebra which is dual to the standard algebra A2. Elements of this algebra are represented by monomials, linear combination of monomials in the letters psi1, psi2, and so on. So the degree of the monomial of such a monomial is given by this formula. Each psi has degree of this form 2 to the power of k minus 1, but the filtration is different. The filtration can be calculated in the following way. Let us define a function alpha 2 of n. So you take a non-negative integer n, and alpha 2 is a sum of digits and two-adic expansion of n. So you write number n in this form, so two-adic expansion, and just add these digits di. The same applies to any other prime number. So, and then you define for monomial psi I, you define its filtration by this formula. So psi I, so the power A1 goes with weight 1, A2 goes with weight 2, and so on. And the statement is that this characteristic sigma 2 of I splits the Buchstabers filtration. It means the following, that monomial psi I belong to the filtration and P, where P is sigma 2 of I. And what is more important, it is a really difficult theorem. You know that if you have some elements of specific filtration, well, it belongs to NP but does not belong to previous one. It is important. Important thing is that if you consider linear combination of psi i's which belong to filtration P, so non-trivial linear combination is still NP. It does not go to NP minus 1. Since we speak about filtration, it could happen. So if you take elements of filtration P, take its linear combination, it can land to the lower filtration, but it does not happen in this case. So this theorem which you see here is that if you consider elements of filtration J and elements of filtration J minus 1, then characteristic sigma 2 allows you to split this embedding of one subspace into another. There is an analogous formula for P greater than 2, and so it's not a good idea to finish talk by non-optimistic thing, but nevertheless I'll do it. So unfortunately then I proved this theorem. I found that this theorem follows from one theorem from John Peter May's thesis. The thesis was not available for a long time because it was non-published. People usually make a reference to his thesis, but it was scanned and put on the internet some time ago, not so long time ago, and I was was not very happy to see that this theorem can be obtained by dualization of theorem by John Peter May, but both proofs, his proof of his theorem and my proof of this theorem, both are complicated. So, well, what we can say else? Just to finish on optimistic note, okay. So I already told you that filtration in dual of Landweber-Novikov algebra is difficult problem. The people knows only n2 and n1, but if you pass to rational numbers, if you want to consider Landweber-Novikov algebra over the rationals, then the filtration was completely calculated, and it was calculated in a very interesting way. Well, let me tell you in a few minutes. So we consider so-called Chern-Dold character. Chern-Dold character can be thought as a functional inverse to the logarithm of universal formal group. So complex cobordism ring is actually a so-called Lazar ring, which has so-called universal formal group law, and logarithm of this formal group law was calculated by Mishchenko. He never published this result, and the result was published by Novikov in his paper, which I already mentioned as supplement. Yes, supplement. But if you consider non-functional inverse to the Chern-Dold character, but just this type of inverse, multiplicative inverse, then you obtain new generators for S star tensored by Q, and this element performs the splitting of filtration into, so if you have NP as a filtration of level pi, this one is filtration of previous level, so you have subspace which is complement. And this is described by this very simple formula. And the tricky part was to find generators which provide you this type of splitting. It was done, and I hope this will provide us with some possibility to obtain new result on cohomology of Landweber-Novikov algebra. So thank you very much for your attention. Let me stop here.
Okay, thank you, Professor. Are there any questions?
Can I have a couple of words?
Okay.
Of course.
Thank you very much, Fyodor Yurievich, for your talk and especially for the history of the Hopf paper where it appeared the notion of Hopf algebra. So
I see your sorry for interrupting you. I found your message in chat. Yes, the paper.
yes, and exactly that's what I want to explain. That exactly in the style of your brilliant history, I wrote down the paper where the Adams spectral sequence really appeared. This is the paper in Contrandu in 57.
1 year before, yes.
And of course in French. It gives the history and the impression of that time, which was yes, 50s. So Frank Adams wanted to present his work to where there were at that moment the center of algebraic topology. So to actually, I think, to Cartan, Serre, and so on. So it gives us a little bit the history of the moment. Thanks.
Okay, thank you.
Thank you so much.
Thank you.